All right, so I think we can start, and I hope you can all hear me well. And so let me first start by welcoming everybody here at this first edition of the seminar of the International Institute of Physics in 2022. So we started a little bit late this year, and the reason for that is basically pandemics. So for 2 years, most of the Brazilian universities, they functioned in the online format, and so it's been 3 weeks now that the students are coming back, and we see again our campus full of students. So the life is coming back to normal. We're very happy to have everybody back again. So, and we also we decided to hold our seminars in the hybrid format. So now we are in the auditorium of the International Institute of Physics, and there are a few people participating, but we hope that this number will grow. And there's also a number of people participating online. So we'll keep these two options during this year. So it is a great pleasure today to introduce our speaker, our special guest. So today we have Sergio Rezende. Sergio, let me make a small introduction. Sergio received his PhD from the MIT in electrical engineering and material science. He spent a few years working as a professor at the Pontific Catholic University of Rio de Janeiro and also University of Campinas. And since 1972, he is a professor at physics department of the Federal University of Pernambuco. So his research
in progress.
His research is connecting theory and experiment in the study of magnetic properties of materials. And in particular, he is an active proponent of spintronics, one of the modern areas of material science. So Sergio also served as in different governing bodies that oversee the development of science and technology in the country. And most notably, he served the Minister of Science and Technology of Brazil from 2005 until 2010. He has a long list of awards, from which I can mention the awards of Bunge and Konrad Wessel Foundations for his contribution to science and science dissemination, the prize of Brazilian Physical Society for his work in condensed matter theory physics, and also outstanding referee award from the American Physical Society. So the title of his talk today is An Endless Samba with Magnons and Phonons. So without further ado, I pass the word to Sergio. Sergio, thank you very much for being with us today.
Thank you, Dimitri, for the invitation to speak today for this selected audience, and thank you for the kind presentation. The reason for the name, Endless Samba, is that magnons and phonos have been dancing with each other for about 60 years, 6 decades, more than half a century. And despite this long history of interplay between magnons and phonos, each year, in the recent years, we had new developments in the field. But before starting the real talk, I feel that I should make a very brief presentation of some basic concepts, because most of the others does not work in magnetism. Well, ferromagnetic materials are materials that have permanent spins, atomic spins, and they have an exchange interaction that tends to make the spin ordered in one direction. Well, then the material has magnetization, and a plot of the magnetization as a function of temperature gives something like this. The magnetization decreases with the increase in temperature, and it goes to zero at a critical temperature, Tc. And one asks, what happens at temperature very much smaller than Tc? Because in the beginning of the 20th century, there was a model proposed by Pierre Weiss that gave an expression for the magnetization. But a few years later, a brilliant Nobel Prize winner made theoretical consideration about the excitation. The question is, let's say that we have a ferromagnet in an applied magnetic field, and as I said, there is an exchange interaction between the spins, and this is the ground state of the ferromagnet. The question is, what are the excited states of the ferromagnet? In the model of Weiss, the excited states were localized spin deviation. It turns out that this is not an eigenstate of the Hamiltonian, and this was shown by Felix Bloch. 1932, that the states, higher temperature, in other words, the excited states, are not localized spin deviations, but they are collective modes. In these collective modes, he called spin waves. Let me present briefly a semi-classical approach and then a quantum approach to spin waves. The semi-classical approach is based on the Landau-Lifshitz equation that says that dm dt, gamma is the gyromagnetic ratio, is m cross the applied field, but also the exchange field. Of course, this equation, since m is a vector, we have to project m in the three coordinate axes. We call the direction of the applied magnetic field, the equilibrium direction, the z direction. So we introduce a variable, mx plus imy, which denotes the transverse magnetization, and the z component of magnetization is approximately the magnetization itself. Well, if we use the equation for the two components and introduce this variable here, we get a very interesting equation. Laplacian of m, the Laplacian comes from the exchange interaction that gives coupling between the spins, and when there is an angle between the spins, the derivative comes in. Plus gamma h, the magnetic field m, I h bar dm dt. See that the equation for the magnetization has precisely the same form as the Schrödinger equation for a particle. This is interesting and has important consequences. With the solution of this equation, simply m0 e to the I k dot r minus omega k t. This is an eigenstate of the system, and the energy is proportional, as it says here. The energy is varies with the square of the wave number, just like an electron in a flat potential. And this, the fact that we have used a variable that mx plus imy means that there is an angle, phase angle between my and mx. The solution is precisely a spin wave characterized by frequency, which is the frequency of precession, a wave number, which is 2 pi over lambda. This is the view of a propagating spin wave in 3 dimensions. There was made available by Carl Patton. So if we solve the equation for the whole Brillouin zone, we have that the energy frequency increases with the wave number. For small wave numbers, it varies quadratically with the wave number, but then it curves like this. And if we zoom the figure here, we have a quadratic behavior, as I said, very similar to what happens to electrons. Omega is the gyromagnetic ratio, H plus dk square. Gamma is 2.8 gigahertz per kilohertz, which means that with fields of a few kilohertz, the frequency of the k equals 0 mode is in the microwave range. And this is important for the experiment that I'm going to, for the first experiments I'm going to show, because one can excite spin waves with microwave field. Now, as I said, this is a view of a spin wave, and this is a simple view of an elastic wave in a solid. The vibration of the atoms, the ions, is an elastic wave. The quanta of spin waves are called magnons. The quanta of elastic waves are called phonos. And one asks, is it possible in a ferromagnetic material to convert magnons into phonos? I'll show shortly that this is indeed possible. Now, how come we can couple magnons to phonos? The reason is that if we have a magnetic material, here are the spins, and if the spins precess, because of the spin-orbit interaction, the precession of the spins couple with the lattice vibration. And the lattice vibration are the phonos. And it turns out that 64 years ago, Charles Kittel was a brilliant theoretician and also a very good writer of books, as you know. He proposed that there was an interaction between spin waves and ultrasonic waves in ferromagnetic crystals, and he proposed an expression for the magnetoelastic Hamiltonian. Actually, his expression is more general than this. We are considering here a simple expression that involves only two components of the magnetization and one component of the displacement vector. B2 here is called the magnetoelastic parameter or magnetoelastic interaction constant. So we have a Hamiltonian to deal with the coupling between the magnetization and the displacement of the atoms, which means the elastic vibration. So what I'm going to show you are results of experiments with some simple explanation, theoretical explanation of three different natures. This one was shown 60 years ago. This one was shown 3 years ago, 4 actually, and this was shown 1 year ago. So as I said, magnons and phonos keep interplaying with each other for several decades. So let's start with the magnetoelastic waves in space in time varying field. Now, I have to introduce you the most important magnetic material for experiment with spin waves, at least with propagating spin waves. This material is called yttrium iron garnet, with this chemical formula, Y3Fe5O12, which is a material that has in the unit cell a large number of atoms, of which 40 atoms are iron ions, which are magnetic. And despite this very complicated unit cell structure, the egg has very small magnetic damping. In fact, it is the material with the smallest magnetic damping known until today. And this material is not found in nature. It was synthesized in 1956 or 7 by Berthaud and Forat, two French physicists. And it was used in the 60s to study propagating spin waves. Look, they are important to study propagating spin waves because a propagating spin wave decays away exponentially with a decay time that is proportional, that is inversely proportional to the magnetic damping. So one needs a material with small damping to have a long time propagation time. In the 80s, Yale was used to study chaos in spin wave. In the 2000, it was used to study Bose-Einstein condensation of magnons. And in the last 10 years, it has been used to study what we call insulator spintronics. Yale is a material that has practical applications. It is used in microwave components and also in infrared components. It's available commercially, the material, and also several devices. Well, the first experimental observation of propagating spin waves was made with Yale in 1962. The author, I'm going to show his paper shortly, used a Yale disk, a disk, small disk with a few millimeter in diameter, half millimeter thickness, made of single crystal Yale. Yale is used in these experiments when it's grown in single crystal form, which is not very difficult to do. The magnetic field is applied perpendicular to the disk. This is what we call a re-entrant microwave cavity. So if the field is applied perpendicular to the disk, and if we look at the magnetic field inside the disk, it has this shape here. It has this shape because of the demagnetizing effect, which is larger in the middle of the sample and it's smaller at the edges because of the form of the dipole, surface dipole. Well, Eschbach, who then worked in a private company, General Electric, GE, Eschbach showed in 1962 that if you use the microwave field in the cavity in the form of pulse, he used pulsed microwave field. This is the microwave pulse that launches the spin wave. He saw several pulses afterwards. Then if you decrease the magnetic field, the delay of these pulses decreased. And the reason is that the spin waves are excited where the wave number is 0. And the wave number is 0, some value of the magnetic field, because as I showed, the frequency increases the magnetic field, and there is a point in the sample for which the wave number is 0. So the wave is excited at some point here at k equals 0, and then since the wave behaves like an electron in a potential, the wave packet moves in just like a particle in a potential field and goes to the other side. When it arrives here, the wave number is again 0, and it launches a microwave pulse because the precessing dipoles actually produce a magnetic field. And as we decrease the magnetic field, the delay decreases because we go to regions of a higher slope. So this was the demonstration made by Eschbach. 1 year later, he made similar experiments, not with a disc, but with a rod, a cylinder. And the experiment, again, is done with pulsed microwave. The pulsed microwave excites a spin wave in one end of the sample. In the other end, there is an antenna. This antenna picks up the signal. The signal is amplified and goes to a scope. And this is what he saw. This is the wave packet produced. I mean, the pulse produces a wave packet that propagates here, this way. And in the other end, this wave packet creates a microwave field that is detected by the amplifier and so on. Well, let's now introduce the coupling with phonos. I don't have the time to present a quantum treatment, so I'm going to just show the results. As I said, the quantum spin waves are called magnons. And like many other type of elemental excitations, the Hamiltonian for magnons has the form H bar omega k, which is the magnon frequency, CK dagger CK, the creation and annihilation operator for magnons. Similarly, phonons have similar Hamiltonian. If we take the magnon-phonon interaction that I showed before, and we make a transformation for the magnetization to the magnon operators, and from the displacement to the phonon operators, one can show that the magnetoelastic Hamiltonian has terms that involve products of the magnon Hamiltonian and the phonon Hamiltonian. And so that the total Hamiltonian is the sum of the magnon, the phonon, and the magnon-phonon Hamiltonian. This parameter sigma k is proportional to the magnetoelastic interaction given by this expression here. So we have this Hamiltonian for coupled magnon-phonos. Notice that this operator, BK plus, is an operator for a circularly polarized phonon. Circularly polarized phonon in the plus direction, and this is the minor direction. So this term here, for instance, represents destruction of one magnon and creation of a circularly polarized magnon with the plus sense. If we use the Heisenberg equation to find the equations of motion, we have this result here. This CK dagger dt proportional to CK dagger, and two terms involve the phonon operators, and we also have an equation for the phonon operators, and for the plus and for the minus. Here are the equations again. We assume a time harmonic variation e to the I omega t, and then this gives a circular equation that gives the solution for the frequencies, and the equation for the frequencies, this equation here. We have three solutions. Three solutions because we have one magnon and two circularly polarized phonons. So there are three elements involved. You can see that if there is no coupling, sigma k is equal to 0, the three solutions are the magnon frequencies and the two phonon frequencies. Now, we can plot this equation. This curve here, if you follow my pointer, is the magnon curve close to k equals 0. So this is a parabolic variation. And the phonon frequency varies linearly with wave vector. Now, notice that I'm showing different colors here. The reason for this is shown as I show you a zoom here. If we zoom this region here, what we have is the following. Here we have a magnon, here we have a phonon. But since the two excitations are coupled together, the solution of these equations are normal mode solution. The particle, the quasi-particle in this curve here, is independent of the quasi-particle in this curve here. Actually, these are called magnetoelastic excitations or hybrid magnon-phonon excitation. So here we have magnon, here is our phonon, and here we have a hybrid excitation. And there is no coupling between the two because they are eigenvalues of the Hamiltonian. So let us ask, how can I convert a magnon into a phonon? Let's say that we excite a magnon with a small wave number using microwave radiation, like this. Let's say that we excite a magnon with a small wave number. If we then do something and the excitation follows this blue curve, since this excitation is independent of since the blue excitation is independent of the red excitation, this excitation will become a phonon. Now, to convert magnons into phonon, it's necessary to break the conservation of momentum or of energy. As I showed here, we're actually changing wave number, so we're changing momentum, but we're also changing energy. So in this situation here, we are breaking both conservation of energy and momentum. So let me show you the first experiment that demonstrated this conversion. It was done by Walter Strauss in 1965. And Strauss used the following. He used a rod, a cylinder of Yale. There is a pulsed microwave source here that produces a pulsed microwave field by this antenna. And then there is a crossed antenna that goes to a receiver. What happens is the following. The magnetic field inside the rod varies like this one because we apply a field along the rod, and the demagnetizing field is larger at the surface, so the total field is smaller at the surface. We put an antenna here, the antenna creates a microwave, and let's say that the field is such that this is the point where K equals 0. This is called the turning point. And then when there is a pulse, a spin wave is excited here, and then it propagates in the magnetic field. But since the magnetic field is decreasing, at one point, the magnon becomes a phonon. This is because the dispersion relation falls, and then it becomes a phonon. And Strauss observed this, several echoes. This is the launching pulse, and this is these are the several echoes, because when the phonon pulse reaches the surface is polished, optically polished, it is reflected, and then it goes back to this point, becomes a magnon again, and it does this until it decays away due to the damping. So this was the very nice demonstration made by Strauss. Now, how if we vary the magnetic field in time, not in space? To vary the magnetic field in time, we place, this is the rod, the rod is in an applied magnetic field produced by a magnet, but we also wind a coil around the rod to produce a time-varying magnetic field because we use a time-varying current. And this receiver here is what we call a tuned receiver. It receives only a pulse only at a frequency given by some tuning circuit, like in a radio or like in a TV set. So this is the microwave pulse. This is the spin wave, the result of the magnetoelastic pulse. And this pulse here is the pulse of the magnetic field. This is the current that we use to pulse the magnetic field in the coil. So let's say that for this magnetic field, we have the dispersion relation here. And then let's say that we apply this current here. The current is a step. The magnetic field had some value here, and then it changes abruptly in time to this value here. But now we use we change the delay of this step so as to put the delay here. And as the pulse, as the step current is here, see that the spin wave echo disappear. The reason it disappear is that as the magnetic field changes to this other value, the dispersion relation comes here, and the spin wave goes with it. In other words, there is a frequency shift of the spin wave, of the magnons. The magnons undergo a frequency shift because the field is varying time. This happens every time that we have a time variation in the propagating media of any type of excitation. So the spin wave would have another frequency here, so it's not received by the receiver. But then if we change the receiving frequency for 1.8 gigahertz, then we see the spin wave pulse, and we don't see the microwave pulse because the microwave pulse has a frequency of 1.2 gigahertz. One can also convert magnons into phonons by the time-varying field. We use the same experiment as Strauss, but while the pulse is propagating, we pulse the magnetic field down like this. So when the elastic pulse returns to this point, there is no turning point. So the elastic pulse goes to the other side, bounces back and forth, just as an elastic pulse, because we have suppressed the turning point, and there is no conversion between back from phonos to magnons. Well, these experiments realized over 5 decades ago and published in a few papers was the subject of my doctoral thesis over half a century ago. So let me show you 2 more experiments. The demonstration of the spins of phonons. Well, the spins of photons is well known. It was actually demonstrated by Raman, who received the Nobel Prize in 1930. 1931, he did the experimental proof of the spin of the photon. What is the spin of photon? A linearly polarized light has no spin, but a circularly polarized light has spin, which is plus or minus h bar. Photon has a spin plus or minus or minus h bar, depending on the sense of rotation of the polarization. How about a phonon? One has never talked about the spin of phonons. So let me show you this experiment. Nowadays, we don't use cylinders or rods for making experiments. It's much better to use thin films. 60 years ago, people did not know how to make a thin film. But today, we know how to make a single crystal thin film with a few micrometers or tens or hundreds of nanometers. We have a YEG film, but we want to create a non-uniform field. So to create a non-uniform field, we use two small magnets, rare earth magnets, placed like this. And the sample is also in a static. This is the field of an electromagnet, and this is the field of two small magnets. And by measuring the field between the two magnets, we have these points here, and we can fit a curve to these points so that we have an expression, a polynomial expression for the field. And of course, the value of the field varies in each point of the film, and it also varies with the applied external magnetic field. So for an applied field of 0.24 kiloerston, the internal field in the sample is given by this value here because of the contribution from the two magnets. And here is the variation of the field. Let's say that we apply a microwave with an antenna. Let me go back a little bit. Notice that there is a small antenna here that when we apply a magnetic field, it creates a microwave field vary with microwave frequency. And this is a receiving antenna. So this is a launch antenna, and this is a receiving antenna. At this point, the magnetic field is high, so the dispersion relation is high, and for this frequency, 3.4 gigahertz, we excite a magnon. So we use 3.4 gigahertz microwave radiation. We excite a magnon, but then as the magnon propagates down the hill, the dispersion relation is lowered, and then it becomes a mixed magnon-phonon excitation. But then at this point here, the excitation has become a phonon. This is a phonon because we are in the linear region of the dispersion relation. It's difficult to see the linear region because we are using a log scale here. It continues to propagate and becomes a magnon-phonon again, and then it becomes a magnon and it excites a microwave at the other end. We have done microwave fields, but I don't have the time to show you. I'm going to show you light scattering experiments. The sample is placed between the poles of the magnet. It is excited with a microwave generator, the continuous wave. We use a laser to shine light into the sample, and we detect the light that goes into an interferometer. Well, as most of you know, light incident on a sample can produce inelastic light scattering, which means light is scattered with a different frequency, and it excites an excitation in the sample so as to conserve energy and momentum. The Stokes scattering, the frequency of the scattered light is lower than the laser frequency, and then a peak appears. This is the peak corresponding to the laser. This is the Stokes scattering, Anti-Stokes scattering is on the other side. So what we do is to excite magnons with microwave and detect the excitation. This is real measurement in the spectrometer. So this is a schematics of the experiment. Light is incident at some angle with the sample. There is a mirror here, and light is reflected, and we have conservation of momentum in the plane of the sample. So by changing the angle of the sample and the mirror, by changing the angle alpha, we change the momentum of the excitation and of the excited magnet. So by changing the magnetic field, we see Stokes and anti-Stokes scattering, and this shows up only at this value of the magnetic field that corresponds to the excited wave number given alpha. So we ask, what is the polarization of the scattered light? The measurement that I showed, the magnetic field versus angle, gives this plot here. If we had no coupling with phonos, the theoretical curve would be this dashed curve. But since we have coupling with phonos, the magnetoelastic dispersion will give this curve here, and we measure the polarization of the light in this region where the excitation is a magnet. And we have an analyzer at the entrance, before the entrance of the interferometer. The analyzer lets only one polarization come through. So look at the intensity of this Stokes and anti-Stokes scattering with the angle of the analyzer. It practically doesn't change. So if we make a radial plot of the intensity, we have circular polarization. This is expected because magnons correspond to the perception of the spins, and magnons produce circularly polarized light. Excuse me. So, as expected for magnons, how we put, as I show here, how if we look at in this region here, where we have a phonon, this is a phonon because it's away from the magnetoelastic region. We also measure a circular polarization. This means that the light scattered by phonons is also circularly polarized. And this is quite a surprise because people have been doing light scattering, Raman and Brillouin, by phonos, and phonos are always linearly polarized. But the difference is that here we are doing light scattering experiments by phonos converted from magnons. And it turns out that, as I showed in one of the early slides, magnons coupled with phonos with some circular polarization. So this demonstrates that phonos can be circularly polarized, so phonos can have a spin. So it's conclusions of this topic. It's possible to generate phonos by the conversion of magnons in non-uniform magnetic field. The light scattered by phonon generated by the magnon-phonon conversion is circular polarization. So phonon generated by the magnon-phonon conversion had a spin, and they have plus h bar moment, angular moment. These experiments were published in Nature Physics 4 years ago, almost 4 years ago. And then I go to the last demonstration of this endless samba between magnons and phonons. Phonon pumping by spin currents. Well, very briefly, spintronics is the area of physics and technology that make use of spin to perform new functionalities. And the electron has a spin. This spin can be up or down. And if one manages to manipulate the spin, one can actually manipulate information. And the spintronics is the field that studies manipulation of currents by spins, by the spin of the electron. What is this interesting for? For several things. I don't have time to review spintronic phenomena here, but let me show you a very simple view of a charge current. Since electron had spin up and spin down, if we can make the electron move with no collision, neglecting collisions along a film like this, the charge crossing a cross section here, the current crossing a cross section is the sum of the current of spins up and spins down, because they both have the same charge in there. Now, how if we have electrons spin up, moving in opposite direction as electrons spin down? In this case, we have no current, no electric current, no charge current, but we have a spin current. We can say that we have a spin current with spin up to the right, or a spin current to the spin down in the other direction. And this is a spin current in a metal. And the spin current has been shown many years ago, can be converted into a charge current. And many spintronic phenomena make use of this coupling between charge current and spin current. Very important effect involving both current is the spin Hall effect, which was predicted theoretically by Diakonov and Perel in 1971 and recovered by Jorge Reich in 1999. Let's say that we have a charge current in this direction, which means electron moving to the right. Since electrons have spin up and spin down, if we have scattering, and if the scattering is sensitive to the spin-orbit coupling, electron will spin up, will go up, and electron spin down will go down, and then this is a spin current. In this region here, we have a spin current, and the spin current is proportional to the charge current. This is the spin Hall effect predicted by these gentlemen. Platinum, which is a metal with large spin-orbit coupling, has a spin Hall angle, the coefficient of this conversion, which is 0.05. Some materials, some complex materials, have a spin Hall angle of 0.5. 0.5 means 50%. So it means that in all electrons in the current, 50% of the electrons go up and 50% go down. Well, in 2002, these gentlemen made another prediction, theoretical prediction. They predicted if we have a ferromagnetic material undergoing ferromagnetic resonance, since spins are angular momentum, they will inject angular momentum in a normal metal film deposited on the ferromagnetic material. This is called spin pumping of a spin current. We can do experiments of this type by doing ferromagnetic resonance. We have a sample inside a cavity, and microwave field excites the ferromagnetic resonance. We can observe the reflection here. And this is the detected reflection in a permalloy film. And my colleague, Antonio Azevedo, and several collaborators, in 2005, they did an experiment with a bilayer film, not YEG, metallic bilayer, and they had contacts at the end of the sample. And by doing ferromagnetic resonance, they measured a voltage across the two contacts. And the voltage varies the material. And this was an evidence of the spin pumping effect. At that time, we were not very sure about how the spin current was converted into a voltage. So we had a question mark in this the title of the paper, but the explanation was given 1 year later. Actually, a spin current, which means electron in the opposite direction in the film, by the inverse spin Hall effect, they will move in the same direction. And so they will produce charge accumulation here, so they produce a voltage. So spin pumping by the magnetization has been studied in great detail. Now, in 2012, this gentleman made spin pumping with elastic waves, phonons. The experiment consists of using elastic transducers. The transducer converts electric signal into phonon in a piezoelectric material, and the phonons propagate in the cobalt, which is a ferromagnetic material that has a platinum cover on top, and they measure a pulse corresponding to the pulse of the phonon. If they reverse the magnetic field, the polarity of the pulse decreases. So this voltage is due to spin pumping by phonons. Well, if phonons can produce spin pumping, in other words, produce a spin current, there should be a reciprocal effect. Spin currents can produce phonon pumping. And this was demonstrated last year with the following experiment. The experiment consists of having a film of platinum, silver platinum, which is a material with a large spin Hall coefficient. A current passes through this through this film. The current is converted into a spin current that goes into the egg film. And what happens here is detected, there is a current, is detected by light scattering. So laser is shining on the pulse, on the film, and we see the reflector to the Fabry-Perot interferometer. So this is the result of the brilliant scattering. This is the laser pulse. This is with no current. This is the magnon pulse. This is the phonon pulse. Phonon of the substrate, GGG. If we vary the applied magnetic field, the whole thing is in a magnetic field, and vary the magnetic field, the frequency of the magnon increases, as it should. It goes from 10 to 18 gigahertz with a field of 4 kilohertz. So here is the spectrum again. I'm going to change the scale here from 0 to 8 counts to 0 to 1,000 counts with no DC current. In this scale, we see no pulse, no scattering. we apply a magnetic field of 1.13 kilovolt, and then we apply a DC current with 10 milliamps, we see no pulse. With 23, with 35, with 41, with 43. There is a pulse, not a pulse, a peak in the Brillouin scattering corresponding to the current above some threshold. We plot the intensity of the scattering, and this is the result. There is no peak until the current approaches some threshold, but then we measure the frequency of this pulse as a function of magnetic field. It does not vary with magnetic field. We change the thickness of the YAG film. Here we have a film with 154 nanometers. Now we have a film with 93 nanometers, and then the frequency is larger. And the frequency does not vary with magnetic field either. So the conclusion is that a peak in the scattering that does not change with field, but changes with the thickness of the sample is not due to magnons, it's due to phonon. And then we published this paper early last year, evidence of phonon pumping by magnonic spin current. In other words, a spin current in YAG, which is produced by magnons, creates phonons by phonon pumping, which is the reciprocal effect of the phonon pump. Well, I don't have the time to show you the theory. There is a theory. The theory involves magnons, involves several things. We use Boltzmann equation to find these solutions. We introduce the coupling between magnons and phonons, and the explanation is this. The spin current in the YAG film is carried by magnons. Magnons can be scattered into another magnon and a phonon, and we can calculate the probability of excitation of phonons by Fermi rule. Using Fermi rule, we show that the change in time of the number of phonons, of the occupation of phonons, is given by this expression, so that when the pumping rate is larger than the relaxation rate, we have excitation of phonons. We calculated the threshold, and the threshold is in good agreement with experiments. We calculate the Fourier transform, and with this we calculate the frequency, and we have, again, in conclusion, it's possible to generate phonons by spin current in ferromagnetic insulators. This process is Gonzaga reciprocal of the spin pumping effect. The effect is explained by two magnon phonon processes produced by the magnonic spin current, and phenomena involving magnon phonon interaction open new possibilities for investigation and application of spintronics. The paper with the theory was published in July last year. As I said, spintronics is a very active field of research because the spins coupled with many different degrees of freedom. This figure is in this paper of 2 years ago, review paper on the possibilities of spintronics. And I cannot end this talk with a commercial of my book published by Springer in 2021, Fundamentals of Magnonics. And the last chapter of the book is a book on magnon spintronics. So I thank you for your attention. This is a photo of a lab, my colleague Antonio Azevedo, who is from Rio Grande do Norte, Fernando Machado, Roberto Soares, and several postdocs and students. I thank you very much for your attention.
Okay, thank you very much, Sergio, for this joyful story and also for fantastic experiments. So let us thank everybody, Sergio, for his nice talk, both virtually and physically. So I think we already have a question. So the first question is from Bhaskaran. Please, you can open your microphone and ask the question. You're
We
still
don't.
muted. We cannot hear you. You need to unmute yourself.
Good morning, good afternoon, good evening to everybody. My name is Bhaskaran. I do not know if Professor Rezende, I met him 50 years ago when I went to ICTP for a school on interaction of radiation with condensed matter. So Rezende gave a beautiful set of lectures on magnons. So I think I have met him once afterwards. So I really enjoyed listening to your talk, and I take this opportunity to publicly acknowledge my sincere thanks to ICTP, which connected me to people like Rezende. And at that time, Erio Tosati also gave a beautiful set of lectures on plasmons. It was in 76 February. So thank you very much. So it's nice to listen to you after 50 years. And when I read the title, the samba, I thought it's a samba between Rezende and magnon and phonon, not between magnon and phonon alone. So I have a short question, a technical question. Recently, there are lots of exciting developments involving Ethereum and Garnet in the context of time crystals, magnetic time crystals. So can you put it in the context of the samba that you are talking about?
Bhaskaran, thank you very much for reminding me of course, I didn't remember because if you had given lectures, I would remember. But since I did not listen to your lectures in ICTP, I could not remember. Thank you for your kind words. Look, in the recent years, in the context of experiments involving two-dimensional materials, there are many examples of things created by different band structures inside the material or near the surface, like in topological insulators, like in vice semimetals, and not many things done with magnons, but many things done with magnetism and with spintronics. The two-dimensional materials, they have another mechanism for converting a spin current into a charge current and vice versa, which is the Rashba-Edelstein effect. So they are really important in spintronics today.
Okay, because this time crystal notion of Wolowik, where you say that like you can break spontaneously the translation symmetry, you can break spontaneously time symmetry. So there were lots of controversies about it. Then finally it was demonstrated that you could have time crystal involving condensed magnons. In fact, Wolowik wrote some papers and some other group about it involving Ethereum and Garnet, the magnon condensation. It's like almost like a Josephson oscillation. You have two Ethereum and Garnets which are weakly coupled. Then the magnon condensate goes back and forth, and it lives for a long time, the coherent oscillation. So which was connected with time crystals. So I was wondering whether, you will comment on that. Thank you.
Thank you. Thank you for the information.
Certainly an interesting story to look in. Let's see if we have other questions. We have a question from the auditorium here. So Sergio, we have about 15 people participating live in our auditorium.
Okay, so thank you, Professor Rezende, for the nice talk. My question concerns about the. You mentioned the role played by interactions of phonon and magnons, and during your talk, you just mentioned the ferromagnetic materials. I mean, you also can find magnons as quasi-particles for anti-ferromagnetic systems. So I was wondering about what is so relevant and the ferromagnetic materials that you can't find at such uh, magnon-phonon interaction and anti-ferromagnetic systems.
Thank you for your question. I didn't quite hear your name, but certainly magnons are present in antiferromagnetic materials. Actually, Ethereum Garnet is not a ferromagnetic material. It's a ferrimagnetic material. Ferrimagnetic materials have properties. They have many magnon bands, but the lower band, the acoustic magnon band, behaves like the one in ferromagnet. They are very useful if one has only microwave frequency for exciting the magnon. Because in antiferromagnetic materials, in the large majority of antiferromagnetic materials, the frequencies are much higher. They are in the hundreds of gigahertz range or terahertz range. But since now people are able to make experiments with terahertz excitation, magnons in antiferromagnets have also been under intense studies. The coupling between magnons and phonons in antiferromagnet is also present, and people have been doing experiments with antiferromagnet. So you are quite right. Antiferromagnets are also nowadays very important for spintronics and also for magnon studies.
Okay, so that was a question from Fabrizio Oliveira. Are there any questions? So I don't see any questions either online nor offline. So I'll ask one question. So this effect of phonon pumping, can you tell how that could be useful in spintronics, for example? How can we use this effect?
Any conversion of a spin current into some excitation can be used because the information in a spin current to be detected, it has to be converted into some other. The advantage of phonons is that they have much smaller damping than magnetic, than magnons. So if one manage to excite phonos that can propagate along a film, not through the film, that will have application, but that's a challenge. We are trying to reproduce our experiments in new samples with different thickness. We are having some difficulties for many reasons, but as I said, converting spin current into another type of excitation always gives you another degree of freedom that can be used for processing information.
Okay, thank you very much, Sergio. So I don't see other questions. Let's see. So let me thank you again. Thank you for your participation, for agreeing to give the talk, and I thank everyone else for participating. And hopefully we continue and we have more participants in the future. So we invite every local participants to come and invite your friends. See you next week with the next seminar of the IAP.
Dimitri, I'd like to ask you one thing. You put me in the mailing list for announcements of the talks.
Sure, absolutely. So consider it done.
Thank you. Thank you for the invitation. I see you.
See you hopefully soon.
See you soon. Bye-bye. Thank you.
Bye.
Thank you, Bhaskaran. Good to see you.